So we've got this. This is groups 1 and 2, right? Then we've got this one, which is group 3 to 12. Can't believe I had to look for that. 3 to 12. Then we've got 13 to 18, or Roman numerals, X, I, X, V, I. Okay. So, the blue part's called the main group elements. So, the blue part's main group. This part here are called the transition metals. So when you do Bohr diagrams, we're talking about basically just the main groups. So if you do the main groups, how many elements are contained total in just the main group? If you counted up all the elements on any period in the periodic table, on any row, how many elements total would it be if it's just the main group? I'm going to do a Bohr diagram then for iodine. Oh, we've got 1, 2, 3, 4, 5. So, okay, so we've got 5 rings around the nucleus. There's my nucleus. Here's my 5th ring. 1, 2, 3, 4, 5, 6, 7. And then my Lewis dot structure. There you go. Just the 7 dots. Okay? Bonding usually happens between elements that are fairly close in electronegativities. Okay? So, Bohr diagram for H2. So draw, remember Bohr diagram is just interested with electrons. H2. So we're talking about a hydrogen atom that has 1 valence electron. How many does hydrogen want? Nope. Nope. How many does it want altogether? Sorry, let me rephrase that question. Altogether, how many does it want? 2. So it wants, like you said, wants to gain 1. It can lose 1. It can lose 1. But it has a tendency to share more than gain or lose. So, for H2, what it'll do is it will position itself, this is a very bad diagram, so that it will overlap so that those 2 valence electrons are actually right between the 2 nuclei, right? It'll line it up, they're each sharing their electrons so that they both end up with 2 electrons. Now, what do you think oxygen? Oxygen's got a total of 6 valence electrons, so how many more is it going to need? 2. And it's going to do it by sharing. So this time, what oxygen is going to do got its inner 2 electrons, then it's got its valence shell, so it will I'm actually quite bad at estimating how far over to put this. Let's do it like that. So it's going to do it so that those electrons are going to be between both. So each one is going to have 2 electrons in the middle between both nuclei. So what happens here is each is gaining 2 electrons by sharing. So hydrogen forms a single bond. Oxygen will have a double bond. Now a covalent bond occurs when occurs when 2 electrons are shared between 2 different atoms. So, if you have one pair or one group of 2 electrons between 2 atoms, it's a single bond. If you have 2 pairs of electrons between 2 atoms, it's a double bond. If you have 3 pairs of electrons, it would be a triple bond, and you don't do quadruple bonds. No such thing. So we're doing single, double, or triple. So if you've got a triple bond, you're sharing 3 of your electrons with 3 of their electrons for a total of 6 shared, okay? All right, electronegativity. So this is a value that expresses the pull one atom has on the electrons in a bond. There's basically like an electronegativity spectrum. So, do you know what a triangle means? A change in, yes, or difference. Difference in electronegativity. This is the bonding continuum. The bonding continuum. So we're going to mark off a couple of places. It goes up to 3.3, only because the highest one is 4, the lowest one is 0.7. So we're going to mark off a couple of areas here. So if your difference in electronegativity between 2 atoms is 0, so you took the high value minus the low value and it is 0, you are considered to be pure covalent. Pure covalent. There's absolutely equal sharing. If you are 0.1 to 0.4, you are considered to be non-polar covalent. So that means there isn't that dipole formed. The difference is small enough that you're nonpolar. If you are 0.5 to 1.7, you are considered to be a polar covalent bond, meaning there's an unequal sharing of electrons. So now we're talking, there are these dipoles. Somebody is a little bit positive, somebody's a little bit negative. And this will definitely affect physical properties, and we're going to get into that. And if you're greater than 1.7, you have ionic characteristics. Now you could actually be ionic, but you could also be covalent. And it's like you're ionic. There's such a difference in electronegativity, it's pretty much like you're a positive and a negative ion. Okay? So greater than 1.7, you have ionic characteristics. And we're going to see how this affects shape, physical properties. Okay, so this is the type of bonding. Covalent bonding is the type of bonding which results when one or more pairs of electrons are shared between atoms. So, Cl2. Cl2. So, we are going to do what I'd like you to do is draw the Lewis dot structure for a chlorine atom, but draw your Lewis dot structure for a chlorine atom. How many more electrons do you want? One. So what's going to happen is the other chlorine is going to share its electron with you, so now you both have 8 electrons around you. If you look at the blue one, it's surrounded by 8 electrons. Its octet is complete, and so is the red one. So, the symbols with the dots, not my yellow circles, that is a Lewis dot structure for the Cl2 molecule. So that is a Lewis dot structure. Now, sometimes we simplify it, and basically that bonding pair of electrons we represent with a short little stick. So Cl is bonded once to the other Cl, and we show our lone pairs of electrons as dots. When you draw electrons, they are always going to be in pairs. If you've got 3 bonds and then a lone pair, don't split up that lone pair, put one on top, one on the bottom, right? If you get something like this, don't do that. Your electrons always want to be shown in pairs in your dot structures. So this is also a Lewis dot structure. That's one and that's one. Either one is acceptable. It's easier to do the one on the right. It's just a couple of less dots and it just gets a little less confusing. A structural formula only shows the bonds. So it'll just be a Cl with a bond to another Cl. So a structural formula just shows the bonds. No electrons, no unpaired electrons. No unpaired electrons. And then, of course, you've got your molecular formula. The atoms and the number of atoms that are present. So this is your molecular formula. They're not all gases. Br2 isn't a gas, it's a liquid. Iodine is a solid. What do you call Hofbrinkel? What do you call Hofbrinkel? These are your diatomic elements. So these are elements like all of the other elements in the periodic table that exist in nature as two atoms joined together. Okay, two atoms joined together. Magnesium as an element is just 1 Mg. Mercury, just 1 Hg. Silver, 1 Ag. Hydrogen, H2. Oxygen, O2. Okay, these are your diatomic elements. All right. So, molecular formula is H2. So we're going to fill this in even though we kind of did it. So, Lewis structure for H2. We'll do both in this one box. You can do like that or like that for your Lewis structure. Structural formula is just that. Oops, it's not just that. Say that. Oops. Just that. H-H. So structural formula just shows the bonds, not the lone pairs of electrons, which there aren't any anyway because it's H2, and the name of this is hydrogen. This is actually hydrogen gas. Okay, so hydrogen. Next one is O2. Oxygen has 6 valence electrons, but it bonds to get 8. So when you draw your Lewis structure, there will be 4 electrons between the oxygens. So you will have 2 bonds. Each one of those bonds, each one of those sticks contains 2 electrons. Then you would put your lone pair of electrons on. We're actually going to do a lesson where I teach you how to do Lewis dot structures from scratch. So right now, just believe me. Okay, so structural formula just shows the bonds, and this is oxygen. The element oxygen, and it is a gas at room temperature. N2. Now nitrogen has 5 valence electrons. So how many more electrons does it need? 3. So it's going to form 3 bonds. So you're going to put 3 electrons between. We're going to put the other 2 opposite because they're negatively charged. They like to be far apart. There's our Lewis dot structure, or there's our Lewis dot structure. And structural formula just shows the bonds. So this contains a triple bond, and this is the element nitrogen as it exists in nature. The air around you is 78% this, N2. Any questions so far? All right, nonpolar covalent bonding involves the sharing of one or more pairs of electrons unequally, but it's still not a big difference. So CH4. Carbon has how many valence electrons? 4. 1, 2, 3, 4. How many hydrogens do I have? 4. Each one brings 1. So this is how each hydrogen gets its 2, and carbon gets its 8. So we have single bonds here. So there's our Lewis structure. Structural formula. Okay, oops. Oh, that's weird. Okay, structural formula, and the name of this, the IUPAC name, is carbon tetrahydride. Carbon because it's a C, tetra because there's 4 hydrogens. It goes by another name, a common name of methane. (2.1). So you always take the small number from the highest number. So 2.5 minus 2.1 equals 0.4. 0.4. So basically, I'll be giving you formulas and I'll say, okay, what's the difference in electronegativity? Is this polar or nonpolar? Well, you calculate the difference. You look at the bonding continuum. Where does it fall? 0.4. This is nonpolar covalent. Nonpolar covalent. Good call on that, Ruth. Okay. Now here, the chlorine gets more of the shared pairs of electrons since it's got the greatest electronegativity. What's the negativity value of chlorine?
3.
So this one's 3. Hydrogen is still 2.1. So the difference in electronegativity is 0.9. So what happens here is the electrons are actually closer to chlorine. So we can show dipoles. So there's 2 ways to show dipoles. So if this was your structural diagram, your structural formula, you can use this little Greek letter with a plus and a negative. Those are dipoles. Hydrogen's a little bit positive, chlorine is a little bit negative. What I like and what you can also do is you make it like a vector. Which direction are the electrons being pulled? Towards chlorine, so we're going to draw an arrow towards chlorine. To make a positive sign, we're going to cross the tail of that arrow, and that right there indicates that its hydrogen's a little bit positive. So vectors, we're going to use them. So these are dipoles. There's a way to show a dipole, and here's another way to show a dipole. So when you have polar covalent bonding, you have dipoles. Oh my God, man, I laughed. I can still teach you everything you need to know about